Assalamu alaikum. Hi everyone. Welcome to our webinar for the webinar that will be presented by Mr. Muhammad Amin, which is entitled Touring is Not Touring. I will start by a 5 minutes presentation, then Mr. Muhammad will continue. First, about Reservoir Solutions. Reservoir Solution is a company specialized in providing technical studies and courses for oil and gas companies and professionals. Reservoir Solutions incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches like PhD and master degrees. Also, we are assisting in writing technical papers and publishment. Also, we are providing technical petroleum courses by industry experts. Also, we provide mentorship programs. For our next course, which will be on 23 on June, reservoir characterization using analysis, routine core analysis, and special core analysis. It's 1 week hands-on workshop. For the course content, will be 1 week and it's designed for senior management and students and also senior engineers and geologists. It includes day one for introduction about coring, day two for rock typing, day three for special core analysis, and so on. The course content will be shared into the Zoom chat. About our webinar today, coring is not boring. The instructor for our webinar will be Mr. Muhammad Amin. Mr. Muhammad Amin is a senior reservoir engineer working in General Petroleum Company in Egypt. He holds bachelor in petroleum engineering and master degree in reservoir engineering. He has for about 10 years of experience into asset evaluation, reservoir characterization, and simulation. He participated in and recently managed many successful field development plans in green and brown fields. Muhammad has a coalition that holds his name for reservoir fluid modeling. He has many publications into several journals and conferences. For webinar rules, please, if you have any question, you can ask into the Zoom chat and our instructor will answer into the suitable time. Mute your microphone and camera. In case that you wanted to have a certificate for attendance, please fill into the form that will be sent into the Zoom chat. For upcoming courses and events, please join our Telegram channel. Thank you all, and Mr. Muhammad, you can start.
Thank you, Abdullah, for this introduction. Welcome, everyone. Welcome, everyone, for our webinar, Coring is Not Boring. Our agenda for today will include 4 items. The first item will be about the core analysis tests. Then we will talk about the field development planning, FDP, and the definition for field development planning. Then we will go for applications for the core analysis into the field development planning, and what is the importance of core analysis into reservoir modeling. First of all, we have several experiments and tests for the core analysis that I think that every domain into the petroleum industry will deal with these experiments, like the reservoir engineers, like the geologists, like the petrophysicists, also the completion and the petroleum technologists will deal or will require some information that will be given by the core analysis experiments. As you can see into that, that chart, we have the routine core analysis. Routine core analysis means routine, that means usual. So I think that every company always do that experiments to determine porosity, permeability, water saturation, and gamma ray. So we will use this experiments to calibrate the well logs. As you know that the interpretation for well logs is dependent on some correlations like R-sheet correlation and so on. So we have some constant into the R-sheet equation. If we don't know anything about our reservoir and just we are using the constants like for A and M and N, so we have a doubt or we have uncertainty into the interpretation for our logs. That one example to use the routine core analysis, okay? Like for the porosity, okay? Like for the porosity and water saturation, okay? Also the spatial core analysis, we have some experience related to the spatial core analysis, like the relative permeability, like the capillary pressure, and so on, okay? So the relative permeability will simulate the flowing of multi-phase. So if your reservoir has a gas together into the pore system, so we wanted to model the ratio for flowing for each phase. So the piece of information that will tell us about that, it is the relative permeability. Will tell us about the distribution of oil and gas, and water, okay? So the capillary pressure is very, very essential into our conceptual model or our modeling for our reservoir, okay? Also for the G&G teams, the phase determination, which is the essential or the initial step into the phase modeling, which is essential step into reservoir modeling, diagenesis, sequence stratigraphy, and so on, okay? So as you can see, that is the types for core analysis experiments, okay? We have routine core analysis, we have the spatial core analysis, and we have some tests that can be included under the spatial core analysis, like the geomechanics and the formation damage tests. But we can separate it into two other types of core analysis experiments. Okay, so that was for the core analysis experiments. What about the FDP or the field development planning? Okay, so if we have a green field, that means that congratulations, you have a new field. So you wanted to develop that field after exploring it by the first and appraise it by the second and third well, okay? So that green field needs to be development. So you will ask yourself, what about the size for facilities? What is the size of facilities? Is it required to have a high separator, a high number of separators, or you can just use a small separator? What if I can use rental separation facilities and so on, or I wanted to have a fixed facilities and so on. Also for the pipelines, all of that will depend on your characterization for your reservoir. What is the volume? What is the stoichiometry into your reservoir? Okay. So that is for the project construction. Okay, so we have other questions related to the production, like the number of wells. What is the sufficient number of wells to develop my reservoir and to have a good or economic optimum production rate? Okay, so what is the number of the wells? Also, what is the optimum distance between wells? What is the optimum distance between wells? Because if you make that distance between wells very short, so the wells will affect each other, and then we will have a decrease into the production due to interference. Also, the well path design. Is it optimum to have deviated wells, to have high measure depth, to have high exposure to the reservoir, or there is no difference between the deviated wells and the vertical wells, or we can also design the horizontal wells, okay, to have maximum or to have to maximize our production. Okay, so all of that will depend on some information. That information, some of this information will come from the core analysis, as we will mention into the next slides. For also the production, the recovery methods. Okay, so we have initially we are producing our reservoir depending on the primary energy for our reservoir. Okay, second, we can support our reservoir by water injection or gas injection. Then into the third phase, we will design EOR methods like using chemical flooding, surfactant, alkaline, and so on. Okay, so all of that methods should require sufficient amount of information and knowledge about our reservoir. Okay, all of that will included into the field development plan, a plan that will start from the day one for our field or our reservoir until the last day into our reservoir. What should I do to have optimum and economic production from my field or my reservoir? So that is the field development plan planning definition. Okay, so now we know the field development plan, how core analysis will contribute into development activities. Okay, let's have some applications for the core analysis into. Please don't annotate onto the slides. Okay, thank you. So we have some applications for the core analysis that will be introduced into the next slides, like permeability modeling, like the phase distribution modeling, like production prediction, and so on. Let's talk about the permeability modeling. All of the wells that we are having into our fields usually having conventional loads, like the gamma ray, like the resistivity, like the neutron density, and in some wells we can also have the sonic load. Okay, these wells or these logs will tell us about the porosity, okay. Also, if we have some advanced logs like the NMR, it will tell us about the saturation, because the saturation that we are calculating from the Newton density and the interpretation for the conventional logs won't include the residual oil saturation, or the won't differentiate between the movable and non-moving saturation. So if you wanted to differentiate between the moving and non-moving saturation, we will go to other tools, other advanced tools like the NMR or the CMR in other companies. So the NMR will tell us about the moving and non-moving saturation for oil and water. Okay, great. Then if you want additional information about your reservoir, like the mobility, you can measure it. You can have a rough estimation, not accurate estimation, just a rough estimation for the mobility from the MD2 tool or the RFT tool. Okay, what about the permeability? What about the permeability? Actually, no log. We don't have until now a certain log that can measure the permeability, Only we can use some tools or some logs to estimate, to correlate, or to try to calculate the value for the permeability, not measuring it. And actually, many engineer and G&G staff will or are thinking that the permeability that is coming from the NMR is measured. No, it is calculated, or it is a result of a correlation, not a measurement. So again, you remember that anything that you are not measuring, you have a doubt in. Okay? So again, the permeability that you are getting from the NMR, you have a doubt into it. Okay? So the certain or the only tool or to measure the permeability, we can or we should have a measurement from a core that will be acquired from our reservoir. Then after that, we can construct a correlation between the porosity and the permeability. Why? Because we don't or we shouldn't have a core from each log, from all the wells that we are having into our field. Okay, so from one well or two wells or three wells, depending on the size and the area for my reservoir and the heterogeneity that we are encountering into our field. Okay, so we will acquire some cores and we will measure the permeability. Then after that, we will construct a relation or a correlation between the permeability and the porosity. Why? To be used into the uncored intervals, into the same wells, and also to be used into the uncored wells. Okay, because we have some other wells without a core data. So we will use the permeability from the core measurement to estimate the permeability into the other cores. Okay, so that is the first method. The second method is that we have already some correlations for the permeability into the literature, like Timur correlation. Okay, and that correlation have some constants. So we will tune the parameters and the constants into that correlation until matching the permeability that is given by the core analysis. Okay, so that is one application for the core analysis. Which is permeability modeling. Okay, and actually the permeability is very, very essential for all the design and for all the planning and for all modeling for our reservoir. Okay, let's have a case study. Or just a question. If you have an oil well, and that oil well is producing from a massive reservoir thickness. We have a high thickness reservoir, okay, like 100 meters or 200 meters, okay, and you wanted to know the production contribution from each interval. Okay, you already perforated all the reservoir, okay, and you want until you want to know the production contribution from each interval, okay? In your mind, or what do you think? What is the best solution to do that? Okay. I want your answer into the Zoom chat, please. Okay, production logging, PLT, yes. Is there any other answers? Okay, so as you said, the best solution to allocate the production for each interval, it's the PLT. So what do you think? What do you think? If the core analysis can provide you with a rough estimation for a contribution for each interval, how we can do that? It's actually called the pseudo PLT, okay? So if you have an interval, and that interval, you acquired a core from that interval, okay? Or you have a well and you already estimated the permeability. You already estimated the permeability for that interval, okay? You will calculate a parameter that is called reservoir quality index, RQI, which is a function from the permeability and the porosity, okay? Then after that, you will plot the RQI over the cumulative RQI. The RQI over the cumulative RQI multiplied by the thickness, okay? So we have here a typo. Okay? So we will plot the RQI versus the RQI over the cumulative RQR versus the depth, okay? So we have here the depth, okay? And we have here the normalized cumulative RQI or which is equal to the RQI over the cumulative RQI, okay? The intervals that having very high slope, you will say that interval will contribute with the majority of the production, For example, that is the case. We have that interval which is only 4% of the total interval. It contributes by 20% of the production, okay? And that method is very, very useful in case that you don't have any secondary porosity, okay? Like you don't have any fractures or bugs, okay? We are talking here about the matrix permeability. Okay, great. What other applications for the core analysis? One of the very, very essential and very, very important for the core analysis is the phase distribution modeling, especially for clastic reservoirs. Okay? When we acquire, if you have a sandstone reservoir, then you acquired a core from that sandstone reservoir, then the sedimentologist will work on description of the phases that we are encountering into our well, okay? Like he will classify that we encountered a channel point part or alluvial or fluvial, delta border propagation, delta border transgression, and so on. Okay, so we determined the phases that we have into one well. Okay, great. Let's correlate the phases with the logs that we are having into all onto all the other wells. Okay, great. Then in the wells that we don't have any core, we can correlate the fish's type versus the logs that, the conventional logs that we are having into the uncored wells. Great. What after that? The point or the next step is to have a conceptual model. Let's have, before having that example, let's have an example for fishes identification from the core data. Like we have ribbled sandstone, or we have laminated sandstone, and so on. So that is just some examples, and we have several examples for the fishes identification from the core data. Okay, after that we can say that into our reservoir, the best or the most likely fishes or sedimentation, or the conceptual model for our reservoir is to have a fan, or a channel, or to have meandering channel, or we have point bar, or we have sand bar, and so on. Okay, so depending on the fishes into the several wells, we can say that, or we can determine, or we can model the depositional environment for our reservoir. Okay, great. So if we don't have fishes modeling, what if we don't have fishes modeling? Okay, so unfortunately that you may have a dry well, especially like if we have complex depositional modeling. Okay, so for example, if a company that successfully drilled an oil well into the center of a channel. Okay, great. So we wanted to drill the next well. Where to drill the next well? Okay, the reservoir engineer, because he doesn't have the piece of information about the depositional modeling, and we don't have a depositional modeling in our company. So we just go to, we will determine the best. We will determine, or we will say that the best distance between wells about 400 meters. Okay, let's go for 400 meters. Actually, when we drill the next well, we will surprised by having dry well. Why? Because the dry well didn't encounter the sand channel. He encountered the side of the channel that will be filled by the shale, not the productive sand. So again, the core analysis is telling you that, please, I am very, very important for your conceptual modeling for your reservoir. Again, also for relative permeability and the capillary pressure. As you know, that the capillary pressure is relation between the saturation of one phase to the ability of multi-phase to flow. Okay, so if into a certain saturation, if we have a higher oil relative permeability than the water relative permeability, we will say that the majority of the production will be into the oil phase, not on the water phase. And in the opposite, if we have a certain saturation, if we have at a certain saturation, we have higher water saturation than the or higher water relative permeability than the oil relative permeability, we will say that the majority of the production will be into the water, phase. Okay. So as you can see, the importance of relative permeability and the capillary pressure. From the capillary pressure, we will know the fluid distribution. fluid distribution means fluid saturation versus the height above contact, which is called saturation height modeling. Okay, so we know the saturation at a certain depth into our reservoir. Then we will use that saturation. We will go to the relative permeability. Then from the relative permeability, we know the relative permeability for oil and the relative permeability for water. Then we will go to construct a fractional flow curve, and then we can estimate the water cut or the water oil ratio. Actually, we have an example to calculate that. Also, one of the essential information about our reservoir, which is rock compressibility. Actually, as you know, that we have different drive mechanisms for our reservoirs, like the depletion, like the aquifer supported reservoirs, like the gravity, and so on. Okay, one source of energy to our reservoir, it's the rock compressibility itself. When we have high compressible reservoir rock, then we will say that we have high energy inserted or high energy encapsulated into our reservoir. So just start the production, then that energy will be reflected into support of the reservoir pressure. Okay, so again, the one source of the energy for our reservoir, it's the rock compressibility. Okay, and actually the rock compressibility is into the material balance equation. Okay, let's have an example to the effect for rock compressibility into support of our reservoir. Okay, 1 minute. Okay, so we have a material balance model for a certain reservoir, and we wanted to predict the reservoir pressure decline with the production. Okay, so I will go to here and run, then plot the reservoir pressure. That is the tank pressure. Okay, then I will save that scenario to be base. Then done. Then go to the reservoir data. Then I will change. You can see that the rock compressibility is 6 multiplied by 10 to power minus 6. Okay, I wanted to lower the compressibility and see what is the effect of that. Let's have it to be 2. Okay, then done. Then again run the. Then let's compare. That is the prediction, and I want to display the tank pressure. Okay, so the black one is the base scenario, which has high relative rock compressibility, and the red one is the current scenario for the lower rock compressibility. So you can see the difference into the decline or the depletion for our reservoir. Okay, so the higher rock compressibility will lead to more support for the reservoir pressure. Okay, again. Okay, so that was for the rock compressibility. Okay, great. Let's also see the effect for relative permeability into the reservoir performance. So I will go to here. Then again, run the prediction. Then I will save that scenario at base. Okay, we already compared between the low and high rock compressibility. Let's compare on the terms of relative permeability. Okay, so base. Okay, then I will go to input and go to the relative permeability. Then I will increase the water relative permeability and see what is the effect. Okay. Then go to prediction. Then let's compare on terms of water cut. That is the base and that is the water cut. Let's go to the current case in terms of water cut. So you can see when we increase the water relative permeability, the water cut increase relative to the base case with the lower water relative permeability. Okay, that is the logic. What do you want to say? I wanted to say that having reliable core data, not just assumption from your experience or from the literature, will enhance your imagination, will enhance your conceptual model about your reservoir, and will enhance your development planning for your reservoir. Okay. Okay, great. What also the application for the core analysis into the field development planning? Actually, when you wanted to tell, or you are telling your management that you wanted to apply EOR project into your reservoir, so you should tell them the expected volume, the expected oil recovery from this EOR project. Okay, actually, if you have a water production, if you have or you miss a lot of oil due to water production problems, so the initial target for the EOR project is to flood and to sweep that oil to your producing wells. Okay, and one of the functions that will govern and will control the amount of oil that will be swept and will be recovered, it's the residual oil saturation. And the residual oil saturation will be determined by what? It will be determined by the core data. It will be determined by the core data and the special core analysis for relative permeability measurement. Okay. Okay. What also? Someone will say now, okay, so the core data is very essential for the G&G staff and the RE staff. What about the completion engineer? What about the production technologist? Actually, for the production technologist, we have a common problem for sandstone reservoir, which is the sand production. Okay, The sand production is a function for the stresses and the strength for your reservoir. Okay, so if you don't know any information about the stresses and the strength for your reservoir, actually you will produce sand, and in some cases you can lose your well. Okay, let's have this stresses and the strength from the well logs. I will say, or I will answer that, okay, the measurement for the well logs will be a result of correlations, not a measurement. So we wanted to calibrate the results from that well logs, like the sonic logs and so on, by the core measurements, like the UCS, or the uniaxial compressive strength. And you can see that the uniaxial compressive strength is a main factor into the equation that will govern the critical bottom hole pressure. So again, the completion engineer will need to know what is the critical bottom hole pressure that we don't want to be or to become lower than that value, because we don't want to produce sand. Okay, so as you can see that the critical bottom hole pressure that is here, if we enlarge or we increase our drawdown other than or more than that, the difference between the critical bottom hole pressure and the reservoir pressure, so we will produce sand. Okay, so again, the core analysis has a high importance even into the completion process for the wells. Okay, let's have a case study that will show you the importance of having relative permeability from core to estimate the water production for a certain well. And also, this case will show you how the importance of knowing the constants into the Archie equation to estimate the water saturation, and then the water production. That case study for an oil well, and that oil well logged by resistivity tool, and we have the resistivity log reading into the reservoir or the oil interval, resistivity reading into water zone, the porosity, and we know that we have sandstone, so we think that the Archie will work efficiently. And we have the relative permeability from a core data, and we know the viscosity for water, viscosity for oil, and we know the beta O, and we know the beta W from the BVT data. Our task in that case is to know the water cut. Okay, great. So we will go to that Excel sheet, very simple Excel sheet, and you can construct it by yourself. So that is the first step, is to determine the water saturation, Okay, so the porosity that we are having about 10%. So in case that we don't know, or we don't have a core measurement to tell us about the M, N, and A, which are the constants for the Archie equation. So in that case, we will use the default values. And in that case, we will say that we have a doubt, we have uncertainty into estimation the water saturation. And for the management, please, we need a core into that interval to estimate or to have accurate determination for the Archie constants. Okay, so for M, we will use the default value for 2, N also, and A. Okay, then the water or the resistivity reading into the water zone. I think that someone is annotating again. Please, Abdullah, if you can prevent that action. Okay. Then the resistivity into a water zone. The resistivity into a water zone is about 3.1, and the resistivity into the oil zone is about 20. Okay, great. So from the Archie equation, we can, or we got the oil, water saturation and the oil saturation from that, from the Archie equation here. Okay, great. Okay, let's use our relative permeability. Let's use our relative permeability. Then I will copy the relative permeability, then paste it here. Okay, so as you can see, that is the relative permeability. Okay, then I will model it by Curie model. Why? We have a rule of thumb. We have a rule of thumb that any data that we are given by the laboratory, or any data that we will use into reservoir modeling or any reservoir calculations, that data should be smooth, Why? Because into, for example, for reservoir simulation, if you are using not a smooth data, that will lead to extra time into running the dynamic simulation. Okay, and also it may lead to some errors and the case won't be finished in the end. Okay, also we have another rule that if you have a data, a point data like the BVT, like the relative permeability, like the capillary pressure, it is better to model that data. Model means put that measurement into equation or in a correlation. Okay, why? Because if you are using that point data into reservoir simulation software, the software will have extra time into interpolating between points, between points. And in the end, you will have extra time in running the simulation. Okay. So for our case, we are having relative permeability. Then we wanted to model that relative permeability by what? By the Curie model. Okay. So we will manipulate or tune the Curie model until having match to or to have minimum error between the calculated or the modeled and the actual data. So I will go to data, then go to solver, then our objective function, that error to be minimized or to be a value of 0 by changing what? By changing the exponents of Curie model. Then I will solve. Okay, so you can see that we have very, very small value for the error, and that is the values for Curie model. Okay, and that is the calculated data. Okay, great. So we modeled now the relative permeability and we calculated the water saturation. So by having the water saturation, we will know the relative permeability. So I wanted to calculate the water cut or the water oil ratio. So I will go to that relation, which is relate the relative permeability, the BVT inputs by the water oil ratio, So I will input here the viscosity for water, the viscosity for oil, the beta W and the beta O. Okay, so here the viscosity for water and the beta for water or oil for water formation volume factor. Okay, beta O, which is 1.15, and the oil viscosity, which is 5. Okay, great. So I expect now that I will have a water cut about 80 or 90%, nearly 90%. Okay, great. So let's say that we are having very oil wet reservoir. Oil wet reservoir will increase the value for saturation exponent. Okay, so let's have it as 5. So let's see. So you will have nearly 100 water cut reduction. Why? Because the higher oil wettability will lead to capturing, to minimizing more and more the movement for the oil phase. Okay. Okay. So again, if you have a doubt into the Archie exponents, if you have a doubt into the relative permeability, so you will have a doubt into the water cut. Okay. Okay. So that is the case or an application for the core data to estimate the production for a certain oil well. Going to the last point for our webinar today, which is the importance of core analysis in reservoir characterization first, then reservoir modeling, then the reservoir modeling. Okay. Before going to reservoir modeling, we should characterize our reservoir. Okay. So to characterize our reservoir, we should have phase modeling, as we mentioned before into the previous slides, how to know or how to determine the phases that you are having into your field. Then, depending on the phases, you can model the phases or the phase distribution into the 3D model. Okay. Also, the porosity. From the porosity, you will calibrate the calculated porosity from the interpretation or the petrophysical modeling from the conventional data or the conventional logs. Also the permeability. We need to estimate the permeability. So if you have a permeability from the core, you can construct a relation between the porosity and the permeability to estimate the permeability. And depending on the distribution of the phases and the porosity, and also the rock types, you can estimate the permeability. Also the saturation model, the saturation height modeling, or the water distribution into your reservoir. You, from the capillary pressure and the rock typing, you can have integrated approach to have dynamic rock types, not just static rock types depending on porosity and permeability, but also having a dynamic rock types or hydraulic flow units in some authors, by some authors. Okay, again, the saturation model will tell you the distribution of water saturation into your reservoir, and for example, depending on that, you can decide the locations for the next wells. You can see just, it is an illustration for the rock types. You have a well and you acquired a core, then you will determine the facies and you will have XRD and you have thin section to know the pore types. And if you want high accuracy, then you will go to the electroscanning. Also, from the permeability and the porosity, you will have the rock types. Okay, every rock type will have a certain relation between the porosity and the permeability. Okay, then by the dynamic or the special core analysis, like the capillary pressure and relative permeability, you will classify that static rock types to dynamic rock types. Okay. Then after that, you will relate the rock types to the conventional logs that existing into the uncored intervals. Okay, to populate it into the reservoir model. Okay, that just for example, if you have a distribution for the facies, by the facies modeling, you will distribute the porosity. Then we wanted to also distribute the permeability. It is a mistake to distribute the permeability just by the distribution mechanisms and geostatistical mechanisms like the sequential Gaussian simulation and so on. No, the permeability is calculated, not distributed. So in case that every facies will represent a certain rock type, so the permeability function will be equal to that relation if the facies equal 1, and if facies equal 2, so we will use another correlation. If the facies equal 3, so we will use another correlation. Okay, but in that case we are assuming that every facies will represent a certain rock type, but in many cases we found that every facies or a certain one facies can have many rock types. Okay, can have many rock types. This slide here, it is the last slide into our webinar. It is just illustrating the integration between the rock typing and the saturation height modeling. And actually it is taken from a certain webinar from the Curix company, just referencing or a citation. So as you can see that we have rock types, we have 5 rock types, then every rock type will have its own capillary pressure and also will have its own relative permeability. So as you can see that if you are running resistivity log, so you will see that the water is increasing, then decreasing, then increasing, then decreasing. So someone will tell you, isn't a logic to have high water saturation into the above, then lower water saturation into the lower? No. Why? Because we have different rock types, and depending on the bore throat of every rock type, we will have a water saturation distribution. Okay, so I think that take the time for questions. Please, if anyone that having any question, drop it into the Zoom chat. How can calculate RQI? Okay, let's go to that case. Okay, so as you can see, that is the RQI or Reservoir Quality Index. Okay, then from that RQI, you will have another column. Okay, if we are assuming that we are working on Excel sheet. Okay, so we calculate you calculated the RQI the RQI into a single column. Then the next column, you will multiply the H or the thickness or the difference in depth between that point and the point before it, okay? So the thickness will be multiplied by the RQI, okay? Then you will have the total summation of all H multiplied by the RQI. Then into the next column, it will be the normalized RQI, okay? The normalized RQI. So the normalized RQI will be equal to the RQI at that depth over the cumulative depth, the cumulative thickness multiplied by the RQI at that depth. Low compressibility means higher depletion. Yes, higher depletion. Please, again, I think that someone that is called Muhammad is annotating onto the slides. Please don't do that. Okay. Is core analysis in carbonate reservoir in carbonate rocks as important as in sandstone silica clastic reservoir? I think that in carbonate is more important. Why? Because the carbonate have higher heterogeneity, higher heterogeneity than the clastic or sandstone reservoir. So if the case that if you have a certain reservoir, a sandstone reservoir in a certain field and a carbonate reservoir in another certain field. So if you are planning to have a core, so for sandstone reservoir, you can core into a single well. But in a carbonate reservoir, you should have a core in several wells, like have 3 wells or a core into 4 wells and so on, depending on the complexity and the differences that you are having on the well logs, because the well logs is the judging tool or the available judging tool that we are having into all the wells. Can you show that exactly we can calculate saturation distribution using the capillary pressure curve? I will tell you some hints because the saturation height modeling is tedious calculations, but you know, so if you have the capillary pressure, you know the capillary pressure curve, okay? Then you will convert the capillary pressure curve to H or to height. How? Because the pressure is the multiplication of height and the density or the difference in density, okay? So you will calculate the height, okay? The height above what? The height above the free water level, okay? So what is the difference between free water level and the oil water contact? Actually, if you are measuring the MDT to MDT readings, or you have RFT measurements into your well, so the point, let's have a whiteboard. Okay, I can have empty slide like that. Okay. Okay. So that is the relative permeability, the capillary pressure curve. Okay. Okay. So you will convert from BC to okay, a curve that is height above contact versus also the water saturation. How? Because the capillary pressure is the difference or the multiplication of the height and the difference in density between the oil and water and so on. Okay. Okay. So we are calling it the height above contact. Height above contact. Okay, so we should allocate the contact that we are having into our reservoir. So how we allocate it? If you are locating, if you are having a resistivity log, so the resistivity log will be high resistivity, then you will have low resistivity. Okay, so at that point we can say that is the oil water contact. Okay, that is the oil water contact. Okay, great. But the height above contact here is not the height above that level, but the height above another level that is called free water level. Free water level. What is the difference between the oil water contact and the free water level? If you are having measurement for the pressure, like having MDT measurement, and you have certain pressure data into oil interval. Okay, so you will construct a straight line. Great. Then if you are having another measurement for the pressure into water interval, and you can see that it is important to have pressure points into the water zone. Okay, then construct that straight line again. Okay, so we have here intersection. That intersection is called free water level. Okay, from its name, it is free. Free means no stress, no capillary pressure. No capillary pressure, so that is the point here. The free water level at which the here. At which we have zero capillary pressure. Okay, that is the free water level. Okay, great. But all that process for one rock type. Okay, so for every rock type you should have saturation height modeling. Okay, because in some cases you can have a rock type into the above and another rock type into the lower. Okay, so you will be surprised that the rock type which is into the above is flooded by water, but the rock type into the lower is still having oil saturation. How is that? Because the rock types different into the saturation height modeling. Okay, and having different capillary pressure. Okay, I hope that it's just a rough explanation about the saturation height modeling. What is the main difference between flow zones, phases, and rock type? Okay, it is a smart question. Okay, let's define first the phases. So the phases mean that we have different phases, okay, and we also have inner or another classification for phases depending on the classification tool. For example, if we are saying that lithophases, so lithophases means we have sandstone, we have carbonate, we have shaly, we have shale, we have shaly sandstone, and so on. Okay, that is the lithophases. If we are saying electrophases, so electrophases, that means that the classification tool that we are using depending on the well logs or the electric well logs. Okay, if we are saying seismic phases, so in seismic phases we can say that phases have high velocity and that phases having low velocity. Okay, if we are saying pycnophases, so pycnophases are biostratigraphic phases, so that phases will be for a certain organisms, a certain creatures that were existing into a certain age, a certain geologic age, like Eocene or Miocene, and so on. Okay, that is the phases. Okay, so phases means the property or the characters of the reservoir. Okay, so whatever the classification tool. Okay, that is the phases. For rock types, we have the first, we have static and dynamic rock types. The static rock type, it is the rock type or the number of points or the number of intervals that having a specific relation between the porosity and the permeability. Okay, so we can say that that phase, we can say that that interval and that interval from a certain depth to other depths having a certain the same rock type or the same static rock type. So all that interval has the same relation between porosity and the permeability. Okay, that is the static rock type. When it comes to the dynamic rock types, so we are talking about the dynamic properties or the interaction between the rock and the fluid. So we will go to the capillary pressure and the relative permeability. So the two intervals which you were saying that they are having the same rock type, so they will be separated into two rock types. Why? Because the interval number one is having different capillary pressure and different relative permeability than the other interval. Okay, so that is the dynamic rock typing. Okay, so what about the flow units? Some authors saying that rock types is the same as hydraulic flow units. Okay, but some authors saying that no, the flow units, it is the rock type into phases number one. Okay, if we have the same rock type into other phases, so we will classify another flow units. Okay, that is the difference between rock type. I hope that it is clear. I think permeability can also be distributed as porosity, pairs to lethal phases or rock types, but needs to be tested by using regression correlation coefficient embedded into distribution algorithm that high enough. Okay, you can try, but I think that the best method for permeability modeling is to calculate it, not just distribute it by the Gaussian simulation and the other mechanisms. Okay. Have you any dummy Excel sheet to calculate Q or QI? I think that it is very easy to calculate. I think that I explained it and how you can construct that Excel sheet. Yes, I think that we have a very good comment here that we can use the seismic data. We have into the seismic data, we had a very powerful property, which is the seismic. It is distributed in all my field, in all our field. Okay, so the seismic, okay, if you are using core data or well log data, this data is located on the well location, not in all the points into your reservoir, but the main power, the main essential or the important or the very powerful property for seismic data is that seismic data is distributed into the 3D, okay, not only on the location for your field. Okay, so you can use the seismic data as biasing property or just a secondary property to distribute the porosity, permeability, and so on. We are talking here about the integration. So if you have the log data, you will integrate it with the core data. Then you will integrate the both of the data sets with the seismic data. So all of that will create the conceptual model for your reservoir. What is the difference between having capillary pressure and not having capillary pressure in oil-water contact? What is the role of capillary pressure for enhanced oil recovery process? Okay, so as we state that the capillary pressure is essentially into the fluid distribution or the saturation distribution. Okay, so that is the benefit for the capillary pressure. Okay, if you don't have the capillary pressure, so we have some methods that will depend on the interpretation of water of the saturation, the water saturation and the porosity. Okay, actually, I think that there was a fantastic webinar with Mr. Steve Coody. Mr. Steve Coody, I think that is the person who invented a method that's called BVW. BVW is a method that can use the interpretation for the conventional looks to the saturation height model. Okay. Okay. So I think that is there any other questions? Okay, thank you all. Thank you all, and hope to see you, inshallah, in next webinar. Thank you.
Sorry for delay. Thank you, Mr. Muhammad, for your presentation and for your webinar. I think that was very, very interesting and informative for everyone that attended today. Also, thanks for all the attendance, for your patience and attending that webinar. Just I wanted to remind you, if you want to have a certificate for attendance for that webinar, you can fill into the form link that will be sent into the Zoom chat. I will send it now. Also, I will send the registration link for reservoir characterization using food data course. So if you wanted to enroll into that course, you can fill into that form. And also, if you want to review the course content, the link will be sent into the Zoom chat. I will send all the links now. Okay, that is the link for registration and course content. Also, if you wanted to have a certificate for the webinar, I will send the link for certification now. And if you need anything, and if you want to join our Telegram channel, I will send the links for all the contacts of Reservoir Solutions. Okay, so have your time. I will keep the meeting open for 10 minutes, and then it will be ended. Thank you all, and hope to see you into next webinar, inshallah.